Imagine you're taking a picture of a speeding race car. You have a choice to make. If you take a really quick snapshot, the car will look super clear and frozen in action. But when the photo is taken quickly, only a small amount of light has time to come in. So, the picture might end up kind of dark. On the other hand, if you decide to let more light in by taking a longer shot, the car might end up looking like a blur because it moved while the picture was being taken. This analogy illustrates a concept similar to the Heisenberg Uncertainty Principle. This trade-off between capturing motion and collecting light represents the Heisenberg Uncertainty Principle, mirroring how the principle asserts that the more precisely you determine a particle's position, the less you can know about its momentum, and vice versa. The Heisenberg Uncertainty Principle, where focusing on one aspect reduces precision in another, is similar to photography. The more you focus on capturing motion, the less precise your image's exposure becomes, and vice versa. In quantum mechanics, the uncertainty principle arises from the fundamental wave-particle duality of matter and light. Similarly, in photography, there's a balance between the particle-like aspects, capturing motion, and wave-like aspects, gathering light, of the photographic process. The Heisenberg Uncertainty Principle has far-reaching implications. It finds applications in a wide range of technological advancements and scientific fields. Modern electronics, lasers, quantum computing, and various scientific pursuits all draw upon the principles of quantum mechanics, which include the Heisenberg Uncertainty Principle. This principle's influence is integral to understanding and developing these technologies and scientific endeavors. For instance, in astrophotography, capturing faint stars requires longer exposures, which might result in star trails due to Earth's rotation. Choosing between freezing stars or capturing their light often involves this delicate balance. Photography's analogy to the Heisenberg Uncertainty Principle showcases how a fundamental concept from the quantum realm parallels everyday experiences. By understanding this analogy, you'll appreciate that uncertainty and trade-offs exist not only in the world of quantum particles but also in the choices we make to capture the world around us through a camera lens. In today's video, we will explore the concept of the Heisenberg Uncertainty Principle, a profound revolution in quantum mechanics. Before starting the uncertainty principle, let's explore the history and the reasons that led to the development of quantum mechanics. During the 7th and 6th centuries BCE, many ancient Greek philosophers like Heraclitus and Leucippus believed in determinism. Later on, Aristotle and the Stoics further explored and elaborated upon this philosophical view. According to them, determinism means that events happen because of events that happened before. In simple terms, determinism says that the way things are now is because of how things were before and how things are connected together. They thought that events were connected by this kind of cause-and-effect chain. In the 16th century, the development of Newtonian mechanics described the physical behavior of the universe using fixed laws. These laws suggest that if we know how things start, we can predict what happens next. This idea reinforces the concept of determinism. So, in the early 19th century, after the success of Newtonian mechanics, the French scientist Marquis de Laplace argued that the universe was completely deterministic. It means that the entire universe operates in a completely predictable manner. According to him, everything is determined by scientific rules. He suggested that we could foresee every event in the universe if we had full knowledge of the universe's state at one specific moment. For instance, if we had the positions and speeds of the sun and planets at one time, we could apply Newton's laws to figure out the state of the solar system at any other time. This idea of determinism seems quite logical in this context, but Laplace took it a step further by assuming that similar laws governed everything else, including human behavior. This idea is known as Laplace's demon or Laplace's determinism. It's important to acknowledge that Newtonian mechanics and subsequent physical theories have successfully described the behavior of the universe to a certain extent. They are based on observations and experiments. However, as scientific understanding advanced, challenges emerged, especially when studying very small things like atoms. An atom's size is just 1/10,000,000th of a meter. It means that if you arrange 250 million atoms in a line, they will only stretch to about an inch. If you are interested in learning more about this topic, you can check out my series on particle physics. You can find the link in the description below. On a small scale, classical physics could not explain everything accurately. This led to the development of quantum mechanics. Quantum mechanics was needed to address these limitations and provide a more accurate framework for understanding the behavior of particles at such tiny scales. The concept of determinism has sparked a wide range of opinions and debates among philosophers, scientists, and thinkers throughout history. Many important scientists agree on the concept of determinism, including Pierre-Simon Laplace, Albert Einstein, and Niels Bohr. However, this concept faced opposition from many individuals who believed that it undermined God's ability to intervene in the world. They felt that if everything was determined by scientific rules, there might not be room for God to make changes and perform miracles. Even though many people opposed the idea, scientific determinism continued to be a widely accepted belief in the scientific community. The concept of determinism continues to be considered and debated in contemporary times as well. Philosophers, scientists, and thinkers across various disciplines continue to explore the implications and validity of determinism in understanding the nature of events and the universe. Around the start of the 1900s, this concept faced strong opposition. British scientists Lord Rayleigh and Sir James Jeans carried out calculations that pointed to a surprising conclusion known as the ultraviolet catastrophe. Hot objects, like stars, might be emitting energy at an infinite rate. According to the prevailing laws of that time, it was expected that a hot body would emit electromagnetic waves, like radio waves, visible light, or X-rays, uniformly across all frequencies. For instance, a hot object should emit the same amount of energy in waves with frequencies ranging from 1 to 2 million waves per second as it would in waves with frequencies ranging from 2 to 3 million waves per second. This idea shows that the energy is given off by hot objects in different ways, no matter how fast the fluctuations are. However, this raised a significant issue. Since the range of possible frequencies is limitless, it implies that the total energy emitted by the hot body would be infinite. This revelation challenged the existing understanding of how energy and radiation worked. The notion of an object emitting an infinite amount of energy just did not make sense and contradicted the principles of science. This realization highlighted that our traditional ways of thinking needed to be changed. The beliefs and assumptions we had held would have to be rethought and adjusted to accommodate the unexpected limitations and intricacies uncovered by the calculations of Lord Rayleigh and Sir James Jeans. This was a pivotal moment that signaled the start of a move away from the strict belief in determinism, which had long been the central foundation of how we understood the workings of the world. To avoid the absurd idea of infinite energy emission, the German scientist Max Planck put forth a solution in 1900. He suggested that light, X-rays, and similar waves could not be emitted randomly. Instead, they were emitted in specific packets he called quanta. Each quantum had a certain amount of energy, which increased with the wave's frequency. E equals h times f. E is the energy of the photon or quanta, h is the Planck constant, a fundamental constant of nature, and f is the frequency of the photon. This equation essentially states that the energy of a photon is directly proportional to its frequency. In other words, higher frequency photons carry more energy than lower frequency ones. So, at really high frequencies, it would take more energy than is available to emit just one quantum. This meant that the emission of energy at those high frequencies would be limited. As a result, the rate at which the object lost energy would be finite. Planck's quantum concept provided an explanation that aligned with what we observed in reality regarding how hot objects release energy. However, the implications of determinism only became clear in 1926, when another German scientist, Werner Heisenberg, came up with his famous uncertainty principle. This principle says that to predict where a tiny particle will be and how fast it is moving, you need to measure its present position and speed very precisely. Heisenberg's uncertainty principle is written as delta x delta p is greater than or equal to h upon 4 pi. X is the position of the particle, and p is its momentum. H is Planck's constant. So, delta x is the uncertainty in position, and delta p is the uncertainty in momentum. A straightforward method to achieve this principle is by illuminating the particle with light. When this happens, certain light waves will be deflected by the particle. This scattering of light will give us information about the particle's position. However, Heisenberg realized that you cannot measure both things very precisely at the same time. If you try to measure one thing exactly, like position, you will end up with less exactness in the measurement of the other, like velocity. This discovery challenged the idea that you could know everything about a particle's future if you knew everything about its present. In essence, Heisenberg's insight started shifting scientific thinking away from strict determinism. There is a limitation to how accurately we can find out the particle's position using light method. We can't determine its position with more precision than the distance between the crests of the light waves we are using. To measure the particle's position more precisely, we need light with a shorter wavelength. But due to Planck's quantum theory, we can't just use an arbitrary amount of light. We have to use at least one quantum of light. This quantum of light, though, causes a problem. It disturbs the particle as we are trying to measure its position, and this disturbance affects its velocity in a way that can't be predicted. What's even more intriguing is that the more accurately we measure the particle's position, the shorter the wavelength of light we will need, and this means each quantum carries higher energy. Consequently, the particle's velocity gets disturbed even more. This leads to a kind of trade-off. The more you focus on measuring the particle's position, the less precisely you can measure its velocity, and vice versa. As we learned earlier that the uncertainty in a particle's position multiplied the uncertainty in a particle's momentum, which is uncertainty in its velocity times the mass of the particle, the result can never be smaller than a certain fixed value. What's remarkable is that this limit isn't dependent on how you're trying to measure the position or velocity or the type of particle you're dealing with. Heisenberg's uncertainty principle is an essential and unchangeable characteristic of the world, indicating that there are inherent limits to how well we can simultaneously know certain aspects of a particle's behavior. The uncertainty principle indeed shattered the classical deterministic worldview and introduced a probabilistic understanding of particle behavior. If we can't measure the present state of the universe with absolute accuracy, predicting the future with certainty becomes an impossible task. This was a significant blow to the idea of a completely deterministic universe. Some might still imagine that there's a set of laws governing events entirely, guided by a supernatural being who could observe the universe's present state without causing any disturbances. Yet, these models are not very appealing to us regular people. The uncertainty principle is a big deal. It was a fundamental concept that led to the creation of quantum mechanics. This whole approach sparked a major change in the field of science. Scientists like Heisenberg, Erwin Schrödinger, and Paul Dirac totally remodeled the way we understand how things work. They built a whole new theory called quantum mechanics, all based on this uncertainty principle. This new theory completely changed how we see the behavior of particles. And even though some parts of it seem a bit weird, it's become the foundation of modern physics. It's influenced everything from how our electronics work to understanding chemistry and biology. In this new quantum mechanics theory, particles no longer have well-defined positions and velocities as they did in the classical world. Instead, they existed in a quantum state, a mix of both position and velocity properties. In quantum mechanics, you can't predict one single, certain outcome for an observation anymore. Rather, the theory offers a range of potential results and tells us how likely each of these outcomes is. Imagine you did the same measurement on many similar systems, all starting in the same way. You would find that the measurement result might be A in some cases, B in others, and so on. While you can estimate how often you'd get A or B, you can't predict the exact outcome of any individual measurement. Quantum mechanics introduces an element of unpredictability into the realm of science. It's like nature's own roll of the dice. This unpredictability is inherent to the behavior of particles at this tiny scale and is a fundamental part of how quantum mechanics operates. Despite the success of quantum mechanics in explaining experimental results, Albert Einstein never accepted the idea that the universe operated based on randomness. He famously stated, "God does not play dice," reflecting his belief that there should be deterministic rules underlying everything. However, most other scientists were more open to the concepts of quantum mechanics because they aligned remarkably well with experimental evidence. Quantum mechanics has turned out to be a tremendously successful theory, forming the backbone of modern science. However, there are still areas where quantum mechanics has yet to be fully integrated. These include our understanding of gravity and the overall structure of the universe on a large scale. The unification of quantum mechanics with the theory of gravity, known as quantum gravity, remains an ongoing challenge in the field of theoretical physics. Despite light being composed of waves, Planck's quantum idea suggests that in certain aspects, light acts as if it were made of particles. It can only be given off or absorbed in specific packets called quanta. Similarly, Heisenberg's uncertainty principle indicates that particles exhibit wave-like behavior in some aspects. They don't have a precise position but rather have a certain spread of possibilities. The theory of quantum mechanics relies on an entirely new kind of mathematics that doesn't describe the real world using traditional concepts of particles and waves. Instead, it's the observations we make about the world that can be understood using these terms. This gives rise to a kind of duality between particles and waves in quantum mechanics. Sometimes it's useful to think of particles as waves, and in other cases, it's better to think of waves as particles. This leads to a concept called interference. Interference is a phenomenon that arises from the wave-like nature of particles, such as light or matter, in certain situations. It's a fundamental concept in physics and is closely associated with wave interference patterns. Interference has been experimentally demonstrated by many scientists, including Thomas Young and Albert Michelson and Edward Morley, among others. Interference takes place when two or more waves come together and interact. This interaction can result in constructive interference or destructive interference. Constructive interference occurs when two sets of waves overlap in such a way that the crests of one set overlap with the crests of the other. In this case, the waves reinforce each other, generating a more pronounced wave. On the other hand, destructive interference occurs when the crests of one set of waves coincide with the troughs of another set. This alignment causes the waves to cancel each other out. This implies that when two sets of waves overlap in such a way that the crests of one set coincide with the crests of the other, they reinforce each other. When two sets of waves can overlap in such a way that the crests of one set coincide with the trough of the other, they cancel out rather than combine to make a stronger wave. It might seem intuitive, but it's been experimentally proven. This phenomenon can be observed with all types of waves, including light, radio, acoustic, surface water waves, gravity waves, and matter waves. An everyday example of interference is the colorful display observed in soap bubbles. These colors result from the way light reflects off both sides of the thin water film that makes up the bubble. White light comprises various colors or light waves of different wavelengths. For certain specific wavelengths, the crests of the waves bouncing off one side of the soap film align with the troughs of the waves reflected from the other side. This synchronization leads to the absence of these colors in the reflected light, causing the light to appear colored. Interference isn't solely limited to light waves. It also occurs with particles due to the duality introduced by quantum mechanics. One of the most famous demonstrations of this is the double-slit experiment. Imagine a barrier with two narrow, parallel slits. On one side of this barrier, there's a source emitting light of a specific wavelength. Most of the light will hit the barrier, but a small amount will manage to pass through the slits. If you place a screen on the other side of the barrier, every point on the screen will receive waves from both slits. However, the light waves coming from the two slits may not be in sync when they reach the screen because they've traveled different distances. This causes some points on the screen to have waves that cancel each other out, resulting in darkness, while other points experience waves that reinforce each other, resulting in brightness. This pattern of alternating light and dark areas is a distinctive feature of this phenomenon. This same pattern emerges if you replace the source of light with a source of particles, such as electrons, that have a specific speed. This means that the associated waves have a definite length. What makes this even more intriguing is that if you only have one slit open, you won't observe any fringes, just a uniform distribution of particles on the screen. Intuitively, you might think that if you open a second slit, more particles will hit each point on the screen, but due to interference, this isn't the case. Even when particles are sent through the slits one at a time, the characteristic pattern of fringes still appears on the screen. This has a surprising implication. Each individual particle, such as an electron, seems to be going through both slits simultaneously rather than choosing just one. This phenomenon challenges our classical understanding of particles as discrete entities with definite trajectories and highlights the deeply puzzling and non-intuitive nature of quantum mechanics. The phenomenon of interference between particles has played a critical role in our comprehension of the structure of atoms. If you're interested in learning the history of particle physics, you can watch part 1 of our particle physics series. The link is provided in the description below. At the beginning of the 20th century, the prevalent view was that atoms resembled miniature solar systems, with electrons, which are negatively charged particles, orbiting around a central nucleus carrying a positive charge. This configuration was believed to be maintained by the attractive force between opposing charges, similar to how gravitational forces keep planets in their orbits around the Sun. However, this model faced a significant challenge. Classical mechanics and electromagnetism, which are prior to quantum mechanics, predicted that electrons would lose energy over time and eventually spiral inward until they collided with the nucleus. This implication suggested that atoms and all matter should quickly collapse into an extraordinarily dense state. In 1913, the Danish scientist Niels Bohr presented a partial solution to this issue. He proposed that electrons might be restricted to specific distances from the nucleus rather than being able to orbit at any distance. He also suggested that only one or two electrons could occupy each of these permitted distances. This concept could prevent the collapse of atoms, as electrons would be confined to filling up these specific orbits with the least energy and distance. Bohr's model marked a significant step forward, but it was only a partial solution. The full understanding of atomic behavior required the development of quantum mechanics, which fundamentally altered how we perceive the behavior of particles at the microscopic scale. This new framework resolved the contradictions and paradoxes posed by classical physics and laid the foundation for modern science. The model Bohr proposed was quite successful in explaining the structure of the simplest atom, hydrogen, which consists of only one electron orbiting the nucleus. However, the model faced challenges when trying to explain more complex atoms, and the concept of limited and specific orbits appeared somewhat arbitrary. The breakthrough came with the development of the new theory of quantum mechanics. Quantum mechanics revealed that an electron orbiting the nucleus could be envisioned as a wave, with its wavelength tied to its velocity. For particular orbits, the length of the orbit would correspond to a whole number of wavelengths of the electron. In these cases, the wave's crests would consistently align, leading to an additive effect. These orbits were the ones Bohr had termed allowed. However, for orbits where the length wasn't a whole number of wavelengths, the wave's crests would eventually be cancelled out by its troughs as the electrons circled the nucleus. This led to a destructive interference pattern, rendering these orbits not allowed in the context of quantum mechanics. This new insight into the wave-like nature of electrons, governed by their wavelengths and the concept of interference, provided a more comprehensive and elegant explanation for the structure of atoms. It extended our understanding from simple atoms like hydrogen to more complex ones, setting the stage for a deeper exploration of the microscopic world using quantum mechanics. Imagine you have a particle, like an electron, and you want to know how it behaves. Normally, we think of particles as either acting like tiny particles or like waves. But in the quantum world, particles can behave in strange ways that are both particle-like and wave-like at the same time. The American scientist Richard Feynman came up with a unique way to understand this. He said that instead of just following one path like a regular particle, let's imagine that the particle explores all possible paths it could take between 2 points. It's like the particle is trying out every possible way it could travel. This concept challenges the idea that particles have a single, definite history or trajectory through spacetime, as classical theories suggest. Instead, in this approach, a particle is envisioned to travel from point A to point B through every conceivable path in between. For each of these paths, there are two associated numbers. One represents the magnitude of a wave, and the other represents the phase in the wave cycle, indicating whether it's at a crest or trough. To determine the probability of a particle moving from A to B, you sum up the wave values for all these paths. When comparing neighboring paths, the phases or positions in the wave cycle can vary greatly. This disparity results in the waves associated with these paths largely canceling each other out. However, for specific groups of closely related paths, the phase doesn't vary significantly among them. In these cases, the waves from these paths do not cancel out. These paths align with the concept of Bohr's allowed orbits, where the wave-like behavior of particles is not destructive due to minimal phase differences between these paths. Each path has a certain probability, like a chance of happening. When you add up the probabilities of all these different paths, something amazing happens. Some paths reinforce each other, while others cancel each other out. This mixing of probabilities is what creates the wave-like and particle-like behaviors we see in the quantum world. So, the sum over histories concept is like letting a particle explore all possible paths, and when you add up their probabilities, you get the strange behaviors we see in quantum physics. It's a way of understanding how particles can be in multiple places at once and act like both particles and waves. This approach offers a unique perspective on how particles navigate spacetime, acknowledging the duality of their nature by considering all possible paths they could take rather than assuming a single trajectory. Using these concepts and translating them into concrete mathematical equations, it became relatively straightforward to calculate the allowed orbits not only in more complex atoms but also in molecules. Molecules consist of multiple atoms held together by electrons that orbit around more than one nucleus. Since the behavior of molecules and their interactions drive the fields of chemistry and biology, quantum mechanics, in principle, provides the means to predict a wide range of phenomena we observe in our surroundings. However, this prediction ability is subject to the constraints imposed by the uncertainty principle. In theory, Quantum mechanics offers the potential to predict much of what we see around us, from the properties of materials to the behavior of chemical reactions. Nevertheless, in practice, the computations required for systems containing more than a few electrons become exceedingly intricate and complex. As a result, our ability to perform these calculations becomes limited, especially for larger systems, due to the immense computational resources and time needed. Einstein's general theory of relativity governs the way the universe's large-scale structure operates. It's classified as a classical theory, which means it doesn't incorporate the uncertainty principle of quantum mechanics, even though consistency with other theories would suggest it should. This lack of quantum mechanics incorporation doesn't pose a problem in most cases since the gravitational fields we experience daily are quite weak. However, the singularity theorem suggests that gravitational fields can become immensely strong in specific scenarios, like black holes and the Big Bang. In such extreme conditions, quantum mechanical effects should play a significant role. This implies that classical general relativity, due to its predictions of infinitely dense points like singularities, indirectly predicts its own limitations, much like classical mechanics predicted its shortcomings by suggesting atoms should collapse to infinite density. Currently, we lack a fully consistent theory that successfully unites general relativity and quantum mechanics. Nevertheless, we have an understanding of several features that such a theory should encompass. These features would likely have substantial implications for phenomena like black holes and the Big Bang, which will be discussed in upcoming videos. For now, we'll shift our focus to recent attempts aimed at unifying our comprehension of the other fundamental forces of nature into a single, unified quantum theory. If you're interested in learning about the fundamental forces that controls the universe, you can check out the video on the left, or if you'd like to explore a complete playlist dedicated to particle physics, you can click on the video on the right.